Hello guys and welcome back. Today we're going to talk about quartz crystals. How they work, how they are made, and their applications. Quartz crystals can be found in almost every electronic device with integrated time measurement. For example, watches, smartphones, or microphones. In the field of digital processing, quartz crystals can be found even more frequently. Wireless data transmission applications are particularly demanding, since the high-frequency accuracy is required for smooth communications between transmitter and receiver. Besides, quartz crystals set the heartbeat in numerous components in automotive electronics. So putting all this together, it is safe to say that life in a modern digitized world without quartz crystals is unthinkable. Quartz crystals are often characterized as a C component and thus only rarely catches the attention of most engineers. The majority see this as a standard component that will always work in its application. The raw materials for the crystals. The chemical formula for quartz is SiO2 and it is composed of only two elements, silicon and oxygen. In its amorphous form, SiO2 is the major constituent many rocks and sand. The crystalline form of SiO2 or quartz is relatively abundant in nature, but in the highly pure form required for the manufacture of quartz crystal units, the supply tends to be small. The limited supply and the high cost of pure natural quartz have resulted in the development of a synthetic quartz manufacturing industry. Synthetic quartz crystals are produced in vertical autoclaves. The autoclave works on the principle of a hydrothermal gradient with temperatures in excess of 400 degrees Celsius, pressures exceeding 1,000 atmospheres. Seated quartz crystals with the desired crystallographic structure are placed in the upper chamber of the autoclave. The bottom of the autoclave is filled with the crushed crystal material in an alkaline solution, thus to serve the crystal growth onto the seeds placed at the bottom of the autoclave. The autoclave is mainly heated from the bottom, so temperatures at the top are lower. The resultant temperature gradients causes thermal convection of the alkaline solution, which dissolves the natural quartz at the bottom of the chamber and deposits it onto the seed crystals at the top. So-called alpha crystals produced by this method can have masses of up to some kilos and are ground in about 20 to 40 days. During this growth process, the temperature should not exceed 573 degrees Celsius. To prevent a phase transition to a different lattice structure that will result in a loss of piezoelectric properties. Nowadays, quartz crystals are an indispensable component of modern electronic technology. They are used to generate precise clock frequencies to control and manage virtually all communication systems and all digital processing systems. They provide an asynchronous reference clock in most electronic devices like watches, computers and microprocessors. That's where we get to the piezoelectric effect. The technical usage of modern quartz crystals is the result of the phenomenon of piezoelectricity discovered by the Curie brothers in France in 1880. Piezoelectricity is a complex subject involving the advanced concepts of both electricity and mechanics. The word piezoelectricity takes its name from the Greek word piezein, meaning to press, which literally means pressure electricity. In fact, a piezoelectric material shows an electrical charge caused by an external mechanical stress or strain. This effect is called direct piezoelectric effect. Quartz crystals in theory and practice. The converse effect also exists, whereby mechanical strains is caused in piezoelectric material by a polarized electrical field. The deformation of the piezoelectric material caused by an electrical charge is called inverse piezoelectric effect. Both effects are strongly linear and reversible. So, piezoelectric effect in a crystal. A quartz crystal resonator consists of a thin piece of piezoelectric material, precisely dimensioned and orientated with respect to the crystallographic lattice. This so-called crystal blanks as a pair of conductive electrodes that are sputtered or evaporated on some surfaces on that crystal blank in a vacuum. When an alternating voltage is applied to the electrodes, the piezoelectric effect stimulates a mechanical vibration, whereby the resonant frequency is defined by the blank thickness. In simple words, we can say that the inverse piezoelectric effect is used to stimulate the resonance of the crystal, and at the same time, the direct piezoelectric effect is used to detect the mechanical movement, ideally at resonance. Advantages of crystals over other resonators. Many different substances have been investigated as possible resonators, and for many years quartz has been preferred material to satisfy the requirements for precise frequency generation. Compared to other resonators like LC circuits, mechanical resonators, ceramic resonators, and more, the mechanical resonator made for quartz materials has been proven to be superior by having a unique combination of properties. These specific quartz crystal properties are both extreme stability over temperature and high repeatability. What makes quartz crystals so important? Key features and the Q factors and stability. The resonant loss of quartz is extremely low, resulting in an extremely high Q factor. The intrinsic Q of quartz is 107 at 1 MHz. Mounted crystal resonators typically have a Q factor ranging from tens of thousands to several hundred thousands, orders of magnitude better than the best LC circuit. The other great key property of quartz crystals is the extreme frequency stability with respect to operating temperature variations, cutting angles, baryoscientific Investigations have been carried out to identify useful orientations of the cutting angle of crystal plates, better known as blanks, for technical purposes and to characterize the resonant properties of the crystal plates that have been cut under certain angle versus the crystal lattice. The so-called AT cut angle is the most common cutting angle to manufacture quartz crystals resonators with a very stable frequency over temperature. AT cut characteristics. The frequency over temperature characteristics resulting from the AT cut as a frequency versus temperature coefficient that can be approximated by a cubic function of the operating temperature. The individual FT characteristic can be precisely controlled. A small variation of the cutting angle can be used to find FT characteristic that is most suitable for the specific applications or operating temperature ranges. However, once a suitable FT characteristic and the corresponding cutting angle has been determined, the cutting angle of each crystal plate or blank should be controlled carefully during production by keeping the variation of the cutting angle as small as possible. It should be noted that due to the cubic function that is associated with the AT cut angle, the resulting FT characteristic is more stable than most of the other cutting angles, which often shows a parabolic temperature characteristic. Due to this property, crystals that make use of the AT cut angle are very suitable to applications requiring high degree of frequency stability over a wide range of temperatures. In addition, the AT cut angle ensures a low aging and high quality factor Q. Low long-term frequency ranges. The long-term drift of the resonant frequency of a crystal is called aging. The aging of a crystal resonator is related to the stability of its mechanical components and to a well-controlled manufacturing process. Resulting from that, mid and long-term stability manifests in frequency drifts of only a few parts per million per year at room temperature. Even low-cost commercial crystals show an aging of less than plus or minus 5 ppm first year. By special manufacturing process steps, low aging rates like plus or minus 1 ppm or less with first year can be achieved. Modes of vibration, cuts, and frequency ranges. Resonant mode. The AT cut crystal resonator uses a thickness shear mode of vibration. The following image shows thickness shear mode of an AT cut crystal. A standing wave builds up inside the crystal blank by reflection at both major surfaces. When traversed, acoustic waves are traveling in the thickness direction. The major mechanical displacement is in the plane of the crystal at a right angle to the direction of the wave propagation. In resonance, an odd number of acoustic half-wave lengths fit into the thickness plane of the crystal blank. Therefore, the thickness is the primary frequency determining dimension in AT-cut crystals. Another important resonant mode is the flexure resonant mode. It is used in the so-called tuning fork crystals. There are other resonant modes like the length extensional mode or the lame mode that might be used for specialized timing and sensor applications. For each of these vibration modes, an optimal cutting angle is used, which controls the frequency characteristics of quartz crystal resonator over the temperature range. AT-cut crystals. AT-cut crystals are commonly manufactured in these frequency ranges: 1 MHz through 60 MHz, operating in fundamental mode, 30 MHz through 250 MHz, operating in overtone mode, 3rd, 5th, 7th, and 9th. As stated before, the required thickness of a blank can be estimated as the knot number of half-wave lengths of the acoustic wave should fit into the thickness plane of the crystal blank. In addition to the thickness of the crystal blank, propagation velocity v of the acoustic wave inside the crystal material is needed to estimate the resonant frequency f. In AT-cut crystals, the propagation velocity is about 3320 m per second. The required thickness d at a given frequency can be estimated as follows. Tuning fork crystals for low frequencies. At low frequencies below 1 MHz, the AT-cut thickness shear mode resonators become too cumbersome and ineffective. Therefore, other modes of vibration are used. The most important resonant mode to create low frequencies like 32,768 kHz is the flexural mode. Typically, a double flexural resonator is used due to the shape with 2 arms. This resonator is called the tuning fork resonator. To stimulate the flexural resonant mode by the piezoelectric effect, the tuning fork resonator must be cut from the crystal bar at a different cutting angle. The resulting characteristics of the resonant frequency or temperature of this special cutting angle being used for tuning fork crystals show the shape of an inverted parabola. Inverted mesa blanks for high frequencies. To generate very high frequencies of up to 300 MHz in fundamental mode, crystal blanks are produced by inverted mesa crystal technology. Inverted mesa is a technology that uses photolithographic techniques to create a cavity thickness with very small thickness into a thicker crystal blank base. By this small thickness, resonance at very high frequencies in the fundamental mode become possible, though not be available using standard AT-cut blanks. Consequently, high clock frequencies can be generated without the need of a PLL multiplier, resulting in lower phase noise than PLL multiplier solutions. Manufacturing of AT-cut quartz crystals. Careful design and production ensures quality. The process to create a reliable crystal requires both a careful crystal blank design as well as a proper setup and control of the production process. The production process includes many steps that should be carried out very carefully. Most of the production steps require well-controlled, clean room conditions. Here are some of the key production steps to produce a reliable crystal. Correct selection and sorting of cutting angle to ensure the desired FT stability. Careful crystal blank design that avoids undesired resonant modes. Appropriate blank polishing for lowest resonant losses. Cleaning of blank surface with best electrode hermetic encapsulation in a dry nitrogen atmosphere for long operating life. Production steps in more detail excluding autoclave. The load capacitance is an important parameter. The electrical properties of a crystal can be described by the so-called crystal equivalent parameter L1, C1, and R1, and the additional shunt capacitance coefficient. As there are many crystal suppliers, so what's the role of a clock signal? The clock signal provides the heartbeat of an electronic system, controlling the timing of events and synchronizing communications, both within and between systems. Role of the clock. Most electronic systems today are based around a microcontroller, an application-specific integrated circuit, or ASIC, or a system-on-chip SoC. This contains one or more embedded processors with on-chip memory, peripherals, and external interfaces. The speed at which a processor executes instructions, the movement of data to and from memory, the operation of peripherals, and the data rates of external interfaces are all driven by appropriate clocked signals. Microcontrollers typically have a clock input with a frequency of around 15 MHz. This is used to generate all different frequencies required inside the device for the bus, processor cores, I/O pins, and other interfaces. Other components in the systems have their own oscillators. A real-time clock, or RTC, typically has an input frequency of 32,768 kHz. Because of this, it can be easily divided by hours of tube to generate timekeeping signals down to 1 cycle per second. This also needs to be very low power as the RTC in the system continues to run, even in standby mode. Ethernet controllers require a high accurate clock, usually with a frequency of 10 or 25 MHz. 3, 2, 1. Accurate oscillators are also important in radio frequency or RF applications, where they provide a stable reference for GPS, radar, and communication systems. It is essential that the transmitter and receiver use the same frequency within narrow bounds so they can filter out unwanted signals and track changes in frequency. The clock technology chosen also needs to balance system requirements such as cost and power consumption against technical demands such as frequency and stability. types of clock circuit. One of the simplest types of oscillator uses a resistor-capacitor resonant circuit. More accurate oscillators can be constructed using ceramic or crystal resonators. RC oscillators. An RC oscillator uses a tuned circuit to define the frequency of oscillation. It consists of an amplifying device, such as an op-amp or a transistor, with the output fed back to the input via a network of resistors and capacitors to achieve positive feedback at a specific frequency. Crystal resonators. To provide a more stable and accurate frequency reference, a crystal resonator can be used instead of an RC circuit. This uses natural resonant frequency of quartz crystal to control the frequency of oscillation. This is very stable due to its extremely high quality or Q factor. Crystals are also small and inexpensive for many common applications. Crystal oscillator operating theory. A quartz crystal resonator uses the piezoelectric effect. This means that its pressure applied, a voltage will be generated across the faces. Conversely, applying a voltage will cause deformation of the crystal. Oscillator circuits. A crystal oscillator requires a high-gain inverting amplifier. This can use a transistor or an inverting logic gate. Crystal oscillators. You can also buy ready-made oscillator modules that contain a crystal and the oscillator circuit. You just need to provide a power supply. This is often the simplest or most cost-effective solution where the device does not have an integrated oscillator circuit. Voltage-controlled crystal oscillator. A voltage-controlled crystal oscillator allows the frequency to be adjusted or pulled within a small range by a control voltage. These are useful in RF and audio frequency circuits, for example, as they allow the system to adjust the frequency to match an incoming signal, compensating for a small difference between the clocks. Temperature compensated crystal oscillator. Although crystal resonators provide an accurate and stable reference frequency, they are still sensitive to temperature. Some applications need much more stable reference. For example, GPS requires a stability of about 0.5 ppm or less. Specifying and choosing a crystal. Some of the characteristics to consider when choosing a crystal are: this should be defined in the data sheet for the crystal or oscillator module. Package. Crystals are available as surface mount devices, STMs, and through hole mounted. Frequency. The specific characteristics of frequency of the crystal specified kilohertz or megahertz. Tolerance. The allowed deviation from the nominal frequency, normally specified in ppm. More accurately, crystals are more expensive. Jitter. The short-term stability of the oscillator frequency. Excessive jitter can interfere with communication protocols and cause an increased bit error rate. Stability. How the frequency of the crystal changes with temperature and aging. The cut known as AT minimizes the variation around normal ambient temperature. ESR, equivalent series resistance. The equivalent impedance of the crystal at its operating frequency, ESR. Values are generally stated as maximum values and are expressed in ohms. The higher ESR requires the oscillator circuit to have larger negative resistance, at least 5 times ESR, to ensure startup. This is affected by the gain and the load capacitance. Lower ESR requires lower drive level and so results in lower power consumption. Lower ESR also means the oscillator starts up more easily. Load capacitance. The external load capacitance must match the specified crystal to ensure the correct frequency of the oscillation. A higher external load capacitance decreases the negative resistance of the oscillator, then increases the startup time and the load. If the load capacitance is too low, it can make the oscillator frequency more sensitive to stray capacitances and board layout. It also increases RF phase noise. Pullability, the amount by which the crystal's oscillation frequency can be pulled from natural resonance by changing the load capacitance. This is important for variable frequency oscillators. In conclusion, RC oscillators are simple, but do not provide the accuracy and stability required by many applications. Those requirements can be met using a crystal oscillator. Designing an oscillator from scratch can be complicated, but you can often use the oscillator built into the device that requires clock. In other cases, an off-the-shelf crystal oscillator module provides a simple solution. There are also available with higher accuracy and stability than integrated isolators. If better temperature stability is required, then temperature-compensated oscillators are also available. And that is it for Quartz Crystals. Again, thank you guys for watching. Please like, share, and subscribe. See you on the next one.